Today I'd like to talk about the geometry of potentials in general, but mostly the two potentials that have the highest symmetry, namely the harmonic oscillator and then the Coulomb field. And we'll put the two of them together in a model that I call the sophomore physics Earth, in which you imagine a perfectly spherical and uniform density sphere called the Earth, and the Coulomb field outside of it, and then that meets another field inside that's a harmonic oscillator parabolic potential. In order to discuss the geometry of that, I want to do a couple little geometrical tricks very quickly. This the sort of an extension of the zigzag method that we talked about in the very complicated freeway collisions at the end of the last lecture. This is a much simpler thing, but it gives you some feeling for geometry in general, but in particular geometry of things that have this marvelous symmetry that makes it possible for us to solve analytically for orbits. And that's all stuff that we're going to do later a little bit in the very next lecture, and then when we get to Unit 5, of course, there's where we get into the details, astronomical calculations and things like that. In any case, as I say, outside and inside meet somewhere, and that geometry has to happen. And other thing I want to do is not just the geometry, but I would really like you to get a feeling for the magnitudes of things, particularly the magnitude of the Coulomb field compared to the magnitude that's an electrostatic field, and to that of the gravity. And I'd like to get sort of little models of how big things are. If the Earth were crushed to the density of a neutron star, or to really ridiculous crushing to the density that we believe black holes have. We'll get that at the very end here as we discuss, as I say, magnitudes of things. So the thing that we'll be encountering then is some monsters. The monsters that we actually work with quite a bit in this department. Quite a few people looking at the galaxies that have black holes at their center. It was a long time before people realized that was true. But also neutron stars are starting to make their appearance in both visible and gravity radiation. So it's worthwhile talking about some of the numbers, just basic elementary stuff with respect to them. And I have a thing called the Neutron Starlet that I'm going to make problems out of. This is very special problems, but imagine that you had some little piece of nuclear matter that was orbiting inside the Earth. It's so dense that the Earth is just cotton candy compared to it, but it would feel the gravitational field, and therefore it would perform an orbit, and that's what we like to see, isotropic harmonic oscillator orbits. What's the basic mechanics and physics of those? Ellipses are important. All of our experimental efforts in spectroscopy now practically seem to involve elliptically polarized light, so that's a connection to the mechanics of the ellipse that we'll be talking about in harmonic oscillators. So among the monsters, the monster that was hitting us when this was done last year was a hurricane called Irma, which never came too much close to the our continent, but this one looks different. This monster is already up to, it's talking about category 4 now, and showing up there late Tuesday or early Wednesday. So the physics of these things, even the simplest physics, which we'll be talking about in a couple of lectures from now, is very interesting. In any case, I keep adding to this some things that are of tangential interest, optical trapping, and some weird things involving putting C60 molecules through gratings and actually seeing them quantum interfere with themselves. That happened quite a bit time ago, but now we're really looking at it in some detail. In any case, on all of these things, it starts with something very simple, just a straight line equation, and I'm going to make a geometrical power series out of this graph. And I will go ahead and try to keep these more or less synchronized, and the idea of proportionality and the use of geometry to basically build parabolas and other objects out of combinations of lines. Let me see if I got this thing on the, go ahead and get this one ahead there as well. Okay, what we've imagining here is just that I've got the line y equals slope times x, and I've got a slope of 1.5 here, and I've got my usual 45-degree line y equal x that is so important for the very first lecture. And I'm asking, well, okay, so I've got that thing. I take the slope value of 1.5 and read it off, and bingo, right away I locate y equal sx with x equal to s as s squared, you see. So we've performed a multiplication. We got a square just by doing the little zigzag, okay? And the idea of this is to keep that zigzag going. Obviously the next step is be aware that this is a geometry that really wasn't available to Newton, at least not unless he could make some graph paper. But be aware, it's hard to make graph paper, right? Starting with nothing, right? He didn't have graph paper, okay? And as I've mentioned, I think already, that's a piece of technology that we now just take for granted. So we're kind of going back and doing geometry over by having that little tool. And let's just see how it works as much as we can here. So let me see if I'm up to date here. In any case, this zigzagging keeps up. Get s cubed fairly easily here, and so forth, even up to s to the fourth. Then we're off the graph paper. That is where this thing would sort of end here if we were trying to just go to larger numbers. But be aware, of course, that you can go and do this backwards, zigzag this way, and now you get things to the negative power, okay? And, well, you remember the monster mash, right? It gets pretty kinky down here, right? Infinitely kinky if you are imagining this thing as perfect lines and all of that. So that is a geometrical series. Now, I'll go ahead and put this one ahead as well. Okay, now, geometric sequence is actually where the sum of that is the geometrical series. Okay, so that is along either axis we've made a series that's quite extensive. Now we do something else, which is shown in that slide down there, and I'll bring this one up to date here as well. There's the sequences, and if I simply put a mark on the staircase at the points that have, well, 1 power, 2 powers, 3 powers, and that's I'll do it here where I can point at it more easily. I have a curve here that is an approximation to a power law, y equal, particularly here s is 1.5 to the xth power. Okay, that's pretty cool. Just a a zigzag way to get a exponential function.
Can I ask a question?
Yes.
How does that zigzag work?
Well,
Like, why does it work?
just the idea that I have a line y equal sx, right?
Yeah.
And the very first, it won't hurt us to go back to where we didn't have all of them. Basic idea is I made a line here with a slope of 1.5, and then I zig from 1, okay, to here, that's 1.5, okay, and then I say y equal 1.5 times 1.5, that's the product. And each zig puts another power on it, right?
Okay.
Is that good question? I wonder how many people are figuring what are we doing here?
So the zigs or the zags or whatever get farther apart, don't they?
Well, you can see they're getting
Right. So what is? So it just so happens that it's always 3.75 over, 3.375 over.
This one is, but the next one
Would be whatever that is.
whatever that is, the fourth power
Okay.
of the number we picked. The magic number we picked is whatever slope I picked.
Okay.
Is that clear? I mean, this is not something I found in any book anywhere. I just thought of it one day and figured it. Now we can use it for other things. We're going to make the inverse square and the square potentials with zigzags. Okay. But this one is kind of neat because once you have it, and let's make sure there are no other questions about this. Once you have it, you can go ahead and you can make it finer. We're pretty coarse right here. These lines are 1 unit ahead. I could easily build it scaled down and get more dots in between there, arbitrary limits. But there I am with the exponential. And while you're at it, remember, you flip x and y, you get a logarithm. Logarithm base s, right? Logarithm base 1.5. So that's, something worth knowing. So just to remind you, this is something that's in the preface. We have these levels of geometrical tools, and I should remind you that the Euclidean level, if you're really talking about Euclidean geometry, you're not allowed to have any indications. You're not allowed to have graph paper. You're not allowed to have anything marked on the. It's just a rule, not a ruler, and a compass. And then you're asked to make, according to Euclid's rules, various polygons and can you trisect an angle? Well, no, you can't. Not exactly anyway. But there are lots of other things you can do that are really quite remarkable. And so that people don't realize that Euclid's Elements as a textbook sold more copies than the Bible. And the Bible sells a lot of copies, right, over those centuries. And so this is a very big piece of our culture, Western culture. Now, meanwhile, the Middle Eastern culture, the Arab Middle East, they were developing algebra. And algebra has the geometry in it, sort of, and the geometry has algebra in it. And what we're really talking about here is analytical geometry, where you put the algebra and geometry together. And that's the beginning of calculus, which is pretty much a Western invention, Newton and Leibniz and the rest of those guys. So anyway, but then it comes time to actually use the stuff, and then you use things like parallel rules. I've got a couple of these here. Since we're not going to make a big deal out of most of our constructions, you don't really do that. But be aware that then you start talking, well, about graph paper, and that's what we're using here in a big way. And finally, just not too long ago, we had calculators, right? Run things out to 13 figures. Just on my watch here is a better computer than we had at Los Alamos for our main scientific work. Anyway, all of these simulations and things are part of our toolbox as well. So all of these things that help us do physics, do theoretical physics, but also real physics in the laboratory, are pretty important. Now, the calculator will give me numbers to, well, this one would go to 12 figures, and here we're seeing it getting the exponential 2.718281828, and it looks like that's a very weird number in the sense that it looks like it's going to be repeating a fraction, therefore rational, but it's not. The next number is not that sequence at all. In any case, using E to build my my geometric thing goes a little faster than the other, but I'll put it up. Put this one back. Put this one up to that point. This one's a little brighter so you can see what the calculator is actually saying there. And the exponential curve, instead of 1.5, now I'm working with 2.718. Now we're going to spend in Unit 10 a good deal of time dealing with the exponential, the complex exponential, and we're sort of going to be getting to it today, but not directly. But the complex exponential that we'll be needing are the ones that make little clocks that describe our oscillators. And that's a really powerful geometrical tool I use in all kinds of things. In any case, here's the exponential curve that would be generated with just E. Now, here's that zigzag thing drawn again now, and you have to realize one of the things that the Western culture discovered fairly late was the ability to draw things in perspective. And you'll find, starting with Caravaggio, the artist Caravaggio, attempted to make paintings that were really realistic. In other words, he was making a painting that we would now call photographic. That is, realistic. Shading and all kinds of things, candle flame would, illuminate the whole painting in just the right way. We're talking the 1300s, 1400s, okay? The 1400s of the Renaissance, but Caravaggio came before that. And perspective, the crew in Athens, they already recognized that was something that was worth doing. Here's a thing with a slope factor s equal 2 that really goes fast. Here's one with 1/2, okay, and I'm taking these things not just up here, but I'm also zigzagging down here and then finishing them with various lines. So this is a perspective view of a hallway, right? And that's another one, and I like to joke about this and say, this is the first day of school perspective of a first grader. You're little, and here's this big hallway, right? But then as a high school student, you come in, you're maybe over 6 feet tall, and the hall's kind of small, right? And it's just a matter of the scale factor for the perspective. And we're going to see this perspective business show up in the diagrams of phase space of oscillators of various kinds, but even harmonic oscillators are going to have interesting ramifications for this business of scaling. And that's why I wanted to get that out of the way just right here. So let's go back to the simple scaling that's associated with zigzagging to make a just plain parabola. And then look at the geometry of parabola the normal way that you would see. That's the way that the Euclid people dealt with it. Here the zigzag is a little bit more sophisticated. This is just a couple of steps to make one point on a parabola, y equal x squared. So basically what you do is you pick some vertical line, and obviously graph paper helps you do that, and then you just go back to the unit line, okay? And once you've got that point, you simply draw a line from there through that point to a point that is on a parabola. That's basically your zigzag line is using this question mark point, and it's giving you question mark squared, kind of like we got 1.5 squared on that second step. So this is just showing it in its job, where now we'll pick other values for that and fill out the parabolic curve, and that's what we're going to be doing here. So let's put this on the other screens here. Blown up, okay, there's the first step right there, and there, okay, and then the next step, of course, is to zig back to the unit, back to the unit, whatever we call 1, all right, and then draw a line through that, okay, and wherever it hits the original line that we started with right here, and this would be 2 squared, minus 2 squared is 4, we've just picked out the point 4, a square, okay, and so forth. This is the way you can generate the parabola, and it's going to work below 1 as well. It's just a little trick. You have to zig backwards, okay, that's no big deal, okay, and find the line that goes through that point, okay, and there's your other parabolic point down there. And I'll go ahead on this screen as well. Okay, so we picked up a couple of points, one up here and one down here on the parabola, and it's pretty obvious what you do to make as many points as you want by this silly zigzag. And we're not even really using graph paper here, except that if we want to know what numbers go with those points, we would need that. In any case, this is a picture of the oscillator potential that I might draw whether I do zigzags or not. And the force, in this case a hook law, in this case a potential, their graphs, Hooke's law being just a straight line, the force as a function of the abscissa x, and here the potential as a function of the abscissa x. Now I've got a 2x line here, to minus 2x, and I've got an x squared here, just the coefficient of 1. But the basic idea is we picked a unit before when we showed the force value increasing and decreasing as we went up and down the various potentials we had in the last lecture. I picked a unit right here, whatever you want. I'm just picking a half here, makes it a little smaller, but it's still giving the right proportion to be normal to the slope vector to satisfy the physicist definition of a force. That is, the force is equal to minus the derivative, but we're doing sort of differences here geometrically and using large values of delta x and delta u at each point. So this one just showing that the force vector for a parabola, if you scale it right, is just the abscissa, scaled by minus 2, and so forth. On either side here is the picture. Okay, so that's the end, for now, of the zigzag approach to this particular thing of force versus potential and the graphing of it. The next stage here, let me put this stuff up there. The next one is a more conventional way to look at the parabola, and put these two together, and you've got a pretty powerful geometry to do things with these curves, which we'll be doing as we discuss the Earth potential inside sophomore physics Earth. Okay, so let's get that in position here and give some names. Now we will be using conic section analysis in Unit 5 in much more detail. There are all kinds of very strange things that really go with the group theoretical manifestation of the symmetry of a Coulomb field and of the oscillator field, and that is something that we should probably wait on. I'm just going to give the most elementary review here of the thing that we need for just discussing the parabolic potential. And make sure that you are aware of the most famous use, and those of you who are astronomers, really, especially radio astronomers that use a parabolic dish, but also, well, anybody in the laboratory that's trying to focus laser light at one point. Very often it's good to have a parabola because the idea is that all of the vertical rays will reflect it just the right way to send the light through it's called the focus. So I'm going to show you a couple of ways to look at this particular structure here and give the right names to various parts of this. The umbilical point, okay, the bottom of the parabola right there. At twice the distance of the focus there sits another line and a circle tangent to that line. The line is called the Directrix. And let's see what else is I need to say. The letter lambda often used to describe that. Let's change this. This is the old name for the lattice rectum. We better be more politically correct here and get rid of that. Lattice radius, please. Okay? You can look at the old books and you get. As I say down here, the old term lattice rectum is an exclusive copyright of the extreme roid ray gyms in Venice Beach, California. So we'll try not to use it anymore. And anyway, radius is a good thing because if this was a circle, that would be the radius. You know, come around like that, right? But it isn't. It's a parabola. It's a radius. The lattice radius is the name that we'll be using. Okay, now let me see if there's anything else here that I need to point out. Oh yes, and this is really important. And this is where I make what I call the kite construction. And that is the distance to the directrix, here to here, to the point on a parabola, is the same as the distance to the focus. No matter where you go, I can swing an arc through the focus, and it better be tangent to the directrix. That's a little more subtle definition of the parabola, okay? But it's a good one, okay? Distance to the directrix, same as the distance to the focus, okay? Well, that makes a beginning of what I call a kite. If I just draw a line between there and then draw tangents and their intersection, which is the center of that, I'll be on the tangent line of this. That's what we want. That's the geometry that we're going to need for a lot of things when we get to discuss orbits, even the simple things that we're going to be doing here. So that's the picture to really look at with regard to our use of conic sections in general, but in particular ones that involve the parabola. Okay, now there's a kite right there. The tangent comes down here, and in the units that we're using, and the units could be this letter P right here, or lambda, which is always twice the P, and it is a point exactly opposite to the focus. And the thing that you should remember about a parabola, if you want to find the focus real quick, you just look for that point that has a unit slope. In other words, the point opposite the focus, and it will be lattice radius away from the focus, has to have a 45-degree slope. And it makes a square kite. Now as you go out further, in particular, if I go from the square kite, which would be right here, to a more like an American kite, I just make a bigger kite as I go up the parabola. But if I begin to take this point inside that lattice radius, closer to this than the lattice radius, I make a more oriental, I should say Asian or something, kite. There's a box kite, but that's a very special case. That's more like what you get when you're inside. It's kind of a little rhombus, a rhomboid kite. Okay? Well, there's a couple of points to notice here. Also notice that the circle of curvature is that circle right there, and its radius is also the lattice radius. That's kind of neat. And then there's, of course, the circle to the umbilical point, which is just plain old half of the lattice radius. Well, these are all things that let you describe the parabola a number of different ways, both algebraically and geometrically. Okay, many questions about that. It's things that will come up later, a little bit later today, but mostly in more advanced discussions of orbits in Unit 5, which is quite a bit away. Okay, now let's look at the Coulomb potential, just quickly and geometrically. And I used to have the class do, and it was a much smaller class, the actual geometry for this. But this is a zigzag construction that, and let's get it on all three screens here, is zigzag construction for both the potential, which is a 1 over r, but we're going to use the letter x because everything's going to be in a cross-section involving the x-axis right here. That'll be the center of the potential. And the unit line, it's a very simple idea of zigzagging again here to get 1 over x, and then you just zigzag one more time and you get 1 over x squared. And this is being done as well for x less than 1 or x greater than 1. Okay, then we'll be making points that lie on the curve that you can see there. And there's another set of points that are green that indicate the force function for a Coulomb field. But basically you follow from the origin through the particular value that you're interested in. Here we're talking about a particular x, say 0.5, okay, and -1, so you come to the unit and you zigzag back. And what you get is that particular point for this value of x minus 1 over x. Well, x is a half, so that's -2, okay? And then go ahead and draw a line through that one to the unit, zigzag back, and now I get 1 over x squared. And for the Coulomb geometry that we're talking about here, very simple case of the unit coefficient, there are the two things that we're interested in: potential, -1 over r, and the force, -1 over r squared. And this is just sort of a thing that shows the geometrical proportions for that. So, this is what we make finally. We make a whole bunch of points for the potential, and then each time we make one of those we do another zigzag, and we make all the points for the force. Is that pretty clear what has happened there? Okay.
I'm wondering why x equals 1? Why are you using that one?
That, very good question, and that's because it works.
Okay.
Right.
Okay.
And
Would picking 2 give you like 2 over r?
finally, what you would do, of course, once you've made it with a 1, then you can put any proportion on you want. Right. So the 1 lets you do the zigzag easily.
Okay.
And we got a nice 1 square, then the proportions are all laid out in a single rectangle. Okay. No compasses needed, right? It's just ruler or just graph paper. You don't even need really a ruler to pull this off. Okay.
How did you notice that it was x equals 1?
Pardon?
How did you know, oh, x equals 1 will work?
Well, the 1 is so special. I mean, I guess that comes from, the group theory, and the unit element of an algebra group is, that's number 1. The main man or main woman in the whole gestalt of the geometry. Now, group theory is just grown-up geometry. Really, like, come down to it. Shouldn't be afraid of it. So, it's these guys. Now, that's what I would have you do, and I would do it on the board with you if we were going to. But we've got more to cover this year than we had. We're luxury of time when this sort of thing was happening. So I'm going to ask you to do a little bit of that in the homework next week. But for now, there's the force curve right there. And what this does, you see, you put your hands on this thing and you get a feeling for how the Coulomb is really long range as a potential. But the force, it falls off pretty darn fast. So you get out to, maybe the end of the board there and you can hardly see the force. But the potential is with you all the way to Fort Smith practically. So that, I think, is important. Now we got to do the inside job as well. Okay, because the sophomore physics Earth has the other kind of high symmetry potential, namely the one that has unitary symmetry. This guy's got orthogonal 4-dimension symmetry. Those are the two groups that are behind the scenes, making it possible for us to do analytic discussions, making it possible for Newton to get famous. Okay? So let's talk now about the actual physics of these things. And in particular, if we're talking about electrostatics, you've all seen this guy, right? How many people know what numbers to put here and here? Anybody?
9.
Yeah.
9
Hi.
10 to the power 9.
8.99, 10 to the positive 9?
Yeah.
Now,
Now, what I would do, and this is, you're going to be teachers someday, okay? You throw them that 4 or 5 figure thing right away, not going to remember, right? But if you put what it is approximately, and that's what I want to do here, I'll put it on this screen down here first, it's 9E9. That's pretty easy to remember, right? So, sure, 8.987551, okay, now plus or minus, we'll talk a little bit about how well that's known. We're working very hard on pushing these decimals out on this one, just like we did the speed of light. But it's really close, 8.98. Okay, you round it off to 3, this is good, this is pretty good, right? And I'd like to do that with as many constants as I can, simply because, well, I have bad memory. And it's getting worse. So, gotta do this. So that's the thing that I want you to be aware of. And not only that, 9E9 is a nice number and all that, okay? But that's huge, monstrous. 9 billion, that's a big number. I mean, essentially we're talking 10 to the 10th. Okay, huge number. And you say, oh, it's because the Coulomb is such a monster. It's not a monster. 1 ampere, which you get 10 of when you start your car, the old-fashioned kind of cars, it's putting through a Coulomb every second if it's 1 amp, right? And it's more like 30 amps. So put 30 of these suckers through every second. Okay, so that indicates to me that the Coulomb is not such a terrible, but it is a terrible number. If I actually assemble a Coulomb of charge in this room, I blow up Fayetteville, right? I mean, it's a monster. Okay, so this is our first monster right here. And you can ask yourself, how much charge is Coulomb, and what kind of units do you have in your finger? How many Coulombs are in there of electronic charge? Presumably balanced, or you've got a bad finger with the positive charge of the nuclei, right? But how many? How much of each of those, you see? So what I'm doing here is just reminding you of your freshman chemistry. We've got the Avogadro number for a mole. We've got a water molecule. You're mostly water, so we can use water as a good indicator of what is going on inside your finger. And a molecular weight here of 18. We got 2 hydrogens and 1 oxygen, okay? And 1 mole, all right, has this many. So I've got to go and I've got to say that if I have a cubic centimeter, that's 1 gram of water, that's 1/18th of a mole, okay? I've got 1/18th of Avogadro's number. That's 0.3 times 10 to the 23. That's a lot of particles, admittedly, okay? And we've got roughly that. That's electrons and protons in there. If we have 10 electrons and 10 protons, we move the decimal over a little bit here. So that works out to about 50,000 coulombs. 50,000 coulombs in your fingertip. Fighting with 50,000 minus coulombs to make your finger stable, so you don't blow up your manicurist. Okay, so that gives you some feeling for what's going on. Now, here's a case of big versus small. What about gravity? Gravitational force. Okay, we're talking MKS here, so we'd be talking about some number of kilograms in say the Earth, and then so many kilograms in your body. Okay, you got some attraction that involves the radius of the Earth. But anyway, this is another one that I put question marks on all the time. Okay, do you know what that one would be? And I mean in a way so that when you're teaching this, you don't snow them with a whole lot of numbers. But this one doesn't have a whole lot of numbers because we don't know this one with anywhere near the precision of this one. And that should be a challenge to you, because with all the astrophysics that's going on now, we're getting better ways to handle this one as well. And in any case, these numbers are so darn important that we would really like to have ways to, well, first of all, deal with them in an elementary fashion. This one, instead of being 10 to the 10th, works out roughly, very roughly, to 10 to the minus 10th in MKS. Okay? It's 2/3 of 10 to the minus 10th. It's pretty good. That's about as far as this is, these numbers in light blue here are sketchy. We really only have this thing to, at best, 5 figures now, and we're trying for 6. So you should be aware that there's work to be done in the gravity department. In any case, instead of being 9 and 9 zeros, this one is a whole bunch of zeros and then 2/3, 0.67. Okay, that's what we're dealing with here as far as the thing that's keeping us on the floor of this room. And we feel this one and deal with this one a lot more than we do directly with this one. But that one's important for us in all of our physics and chemistry. Okay, now, the real measures of any of these is not just the force, but also the potential, the potential thing here. And again, it's the same constant. It's just that now I'm going to be having r to the first power instead of to the second power. And if it's the coulombs I'm worried about, then I can take this potential here and actually figure out how much work I'm getting out of, or how much of a bomb I'm going to be making if I put a whole bunch of these coulombs together and say a unstable nucleus like uranium. These are all things we can calculate now from this big number here. Now, just to get the sort of nomenclature down, nuclear size is so many, 1, 2, 3, 4, maybe 10, 20, and so on, as you go through the periodic chart, or the chart of nuclides. Femtometer, how do you pronounce that? Femtometer is so much what I hear all the time, okay? Meanwhile, atomic size, okay, hydrogen atom has a diameter of 10 to the minus 10th. That's that's 10 angstroms is a nanometer. This is 1 angstrom that we're talking about for the hydrogen diameter, or 0.5 angstroms for the radius of the wave function. And of course the wave function's got this funny exponential shape to it, so you have to say, you have to specify, if you want it exactly, where you draw the line for that. But this is all just a rough description of these lengths. So we're comparing here atomic to nuclear. Now, FM is a perfectly good shorthand for it, but so is capital FM, because this particular unit is also called the Fermi. It's 10 to the minus 13 centimeters. That's the same as 10 to the minus 15 meters. So 1 Fermi, and that's not a picture of him, but I'm just imagining here that we're talking about a nucleus of some other atom beside hydrogen, which only has a proton, but something in the middle of the periodic chart. I've got something with a few, say a dozen, Fermis for its diameter, or radius, I haven't said which. So you get this, and this is an amazing piece of classical mechanics that Rutherford did by throwing alpha particles at gold atoms and noticing how they scattered off of them as though there was just a single tiny point at the center of the atom. The atom being hundreds of thousand times bigger in terms of its electronic size than the nucleus, and that was a big surprise. I mean, you can imagine what a ruckus that made, and Rutherford is a very famous name because of that. But now it's time to, get that into your head and realize how much empty space these atoms and molecules have, and that so much of the matter is packed into the nucleus, absolutely packed. And so when you make a neutron star, you get something that's really dense. So I make this point here that the nuclei radii, and let's get all of this thing going here on the same screen. I keep forgetting to do that. But the basic ideas are that if the nuclear radii are 100,000 to maybe 1,000,000 times smaller than the atomic, that's chemical radii, the molecular radii, then the nuclear energy that's packed there is 100,000 to 1,000,000 times larger than what you get if you're doing a chemical, say, explosion. If you're talking about blowing up TNT or some nitrogen explosive of some kind, that's Coulomb repulsion and makes a pretty big bang and kills a lot of people. But this one is 1,000,000 times more. Okay, and so you get a feeling there for how much energy you get when an unstable nucleus splits, and that's nuclear fission energy, which is powering our nuclear power plants, as you know. Now, I should probably remind you that when people talk about that energy, they also always say, well, that's E equal mc squared. But good luck using that to figure out how much energy you get, right? You can't measure those masses accurately enough to get a good reading on that. So this is the thing that's giving you that number. Okay, that 9E9 is at work there, not mc squared. We'll come back to Mr. C squared a little bit later. Okay, now here's a quick thing that I need to make a point about. We're doing things in an elementary fashion, and when it comes to describing the mechanics of a Coulomb force of any kind, electrostatic force, or else the gravitation, and that's what I'm aiming at right here, is the gravitational one. And it's the ideal inside of the sophomore physics Earth. But I start here kind of the way Newton and others did. This is a geometrical approach to Gauss's law. Basically, the idea is that if I were sitting on a planet right now, and it's fun to imagine that we had, as a planet, a great big shell, all the mass is somehow really packed. So I've got the shell is about this thick, okay? And there's a manhole cover in the middle of this room. I lift up the manhole cover, everything looks dark in there. What I can do is lower myself into that manhole cover, right, up to, say about there. And if this all works out, this geometry's right, I can let go. And I'll just sit there, right? Inside this shell, you're weightless, right? Now what you don't want to do is push like that, because then you're just going to start moving and, oh no, I'm flying out into the center of this thing. I'm gone, right? But I could just be floating. If the Earth were a shell and had a manhole cover, this is all fiction, but it's fun to do this for physics, right? Think about that. Now, what that means then is, no matter what shell I use, it's always going to be weightless inside. This is the basic idea. This is a sort of the spherical thing here. And the idea is, the geometry of this is that, well, how can it balance? I have only a tiny little bit of mass here, but it's closer by some proportion. And the area is this thing squared, and that's the force law for gravity. So even though this is smaller than this by some proportion, so is the distance squared proportional. So this particular part right here exactly balances that little piece there if it took everything else away. But then it does the same thing for every point that's opposite that point that's u. Okay, so that's a very, as I say, hand-waving derivation of the geometrical proportional cancellation that's going on here. But what that means is that at any point, if you're inside this Earth, and I'm going to be imagining a neutron starlet that's happily dancing around inside the sophomore physics Earth, at radius r, which I'll call r lesser, as compared to the entire object, and this is the mass that lies below that particular radius. And that's all you have to worry about. The gravitational force at that radius is just that of this little core that's below it. That's assuming uniform density, which Earth is not. So when you use that argument, then you can say, okay, it's massless, r-less squared, and then you just figure out what that is. You put a 4 pi over 3 in numerator and denominator. Now you're talking about the volume, so you can put this in terms of the density of the Earth, modulo 4 pi over 3 And that's the equation that you'll have for the force inside that. In other words, the force inside that is Hooke's law. First power. Okay? And there's the actual numerical value for it. So that's what we need in order to do our orbits inside the Earth. We're going to have this fanciful story about a neutron starlet orbiting inside the sophomore physics Earth. Now at this point, it's probably a good idea to put some of the, I'm sorry, didn't mean to hit this particular computer, but that's what I want right there. Here's a couple more constants, I should say 4 more constants, that have approximate values that are pretty easy to remember. The Earth radius, 4 figures accuracy, okay, that's fine, but eventually you're going to have to worry about some mountains and stuff here and there. If I just go to 2 figures, 6.4 times 10 to the 6 meters, that rolls off your tongue a little better than this. And then there's 59722, well that's 6 times 10 to the 24th kilograms, that's the entire mass of the Earth, just to a couple figures, okay? Now the Sun does pretty well as well, it's 6955, well that's pretty close to 7, isn't it? 7 10 to the 8th compared to 6.4 times 10 to the 6th. It's a big ratio. We're tiny compared to that guy. And the mass, even more so, but it's also pretty easy. 2 times 10 to the 30th. Okay? So for our work here, just if you want to impress people at physics conferences, these are numbers that you keep in your head, right? So you can, this is what Feynman used to do, okay? Impress people. He's so quick at figuring out things. Fermi was even better at it. He really had all of these constants in a nice form and was able to do it. So this is what we need to discuss. Now we're kind of running out of time a little bit here, so I'm going to go pretty fast with this. But I do want to point out that when you use that kite construction to just make lines using a rectangle, the details that I'm not going to go into right now, but this is a different kind of construction than we're used to. This is construction by envelopes, and we're going to make a big fuss about that later on. But mainly for now, I'm interested in the fact that the slope opposite the focus of the parabola here, and the slope is 1. So everything is, remember I'm taking that 1, right? So I'm absolutely guaranteed a slope of 1 here. That means the focus of the parabola that describes the potential inside the sophomore physics Earth is right there. Okay? So using the kite geometry and all of that, I can very quickly show that this is the point right here. That is the bottom of the potential if you can move freely, like a neutron star. It doesn't see the Earth as really any impediment at all. It's just fluff, and it can orbit, and we're going to be studying those orbits and making some numbers for them. So, and then I'm sorry I used that wrong. It's the lattice radius. Okay, but that is the geometry that we're interested in for inside Earth. Meanwhile, outside Earth, there are the 2 that we looked at before. Okay, and there's the kite, just to remind you what's going on there. Okay, the next part of this, and I'm going to go through this fairly quickly because it's stuff we can come back to later on, but I just simply want to list all of the essential physics that you would want to have at your fingertips if you were describing what happens to things that are orbiting outside, things that are orbiting inside. You can make a lot of headway. And here are just the geometrical units, where the space coordinate x has this as 1, okay? And now we're going to make it something in MKS, namely R, Earth. That's the symbol for Earth that's most used. This is the surface gravity at the radius of that Earth, squared, the Coulomb force law. And here I'm looking at the potential energy using those same, first of all, the variables that have a unit for our outside radius of the Earth, and then you have to put this factor in there to make the same equations that are in MKS variables. So the scaling relation is simply this, and then that gives this, and all of the formulas that we're going to be putting down here have had this done to them to get the things. Now, escape velocity, okay? You come in on this potential, okay, crash right there, okay, from infinity, okay, well, not infinity, it could be Fort Smith, but that seems like infinity, this graph. I'm going to come in here with a velocity that is the escape velocity, but I'm unescaping, right? I'm coming from very far away and crashing here. Time reversal is I send this thing out and it goes to infinity. So I have the kinetic energy here equal to the potential, right? That's the way you find out what the escape velocity is. So let's go ahead and do that. That's velocity escape is the square root of something. And this is, I'm going ahead on this one as well. I'm going to mostly use these two screens for all of this all of these formulas. Okay. So now inside it, this is the equations that have the inside. This is the one where you have the parabola, and basically it has to be at 1/2. That's the two there. The bottom of the parabola relative to, if we were to imagine the origin was right there, gives you this thing. And then we have an extra -3/2 to there. So that's the potential energy, and the escape velocity that works out for this one in MKS units is about 11 kilometers per second. It's about 7 miles per second in English units. And then to go from the bottom of this is, and this is kind of interesting, there are really 3 steps on these diagrams when I get them all up here. 3 steps from living, sitting still at the center of the Earth. Then there's a certain amount of energy it takes to climb up and be sitting right there at the outside of the Earth, okay? And then the same amount of energy, I'll make this short here, the same amount of energy to go to the next step, which is to be orbiting the Earth, skimming at the radius, circular orbit at the altitude relative to the center of the Earth's radius, okay? And then to completely escape is the same unit again. So there are 3 steps, you might say, 3 steps out of hell to heaven, okay? Heaven being infinity with zero potential. I find that to be quite beautiful, and I don't see it in any text. Has anybody ever seen that particular a way to put the whole story together? 3 steps, okay? Now, of course, if this was a quantum mechanical problem, these are energy levels. Okay, there's 3 of them to get out of the center of a uniform charge, say, charge density. Okay, well, inside and out, the surface orbit right there, that particular energy is obtained fairly easily just by using the centrifugal mass times velocity squared over the orbit radius, which is the radius of the Earth, okay? That should be, that mass, mu, is the mass of the particle we're actually imagining, orbiting mass mu, okay, doing the orbit. And then there's the force that's holding it radially, good old Coulomb, with the product of the mass of the Earth and whatever mass the satellite is, this orbiter. Okay, so orbital kinetic energy equals that. That's a very quick thing you get from the centrifugal force equation. And what else? Subtract that, get a orbital E total, which is that. And that, as we say, is this energy the second step here. Okay, first step, second step. Well, that's the actual numerical value, MKS units. Okay, this gets sort of busy after a few more of these formulas. Orbital angular frequency, that's of interest when we talk about this is an oscillator. Okay, this is a harmonic oscillator. You punch this thing, and there's a certain frequency that it's going to ring at. We get hit by a big meteorite, there's going to be that ringing going on for maybe months. I hope that doesn't happen, because it's going to be a big disaster. But it's happened already a number of times. We've got lots of evidence of major hits on this planet. And it rings according to the frequency that we're talking about right here, you see. So all of these calculations of various periods, and this is the one, of course, that we'll be working with. 84 minutes is a typical orbital frequency if our satellites cruised at 0 altitude, which of course you can't, because there's an atmosphere here, right? So you go up to what John Glenn had to go to orbit the first time, or the Russians that came before him. They're making an orbit in about 90 minutes. But if we were a completely vacuum place, of course we wouldn't be here. But if it was no atmosphere at all and you just got the thing going fast enough, that's fast enough to orbit, skimming the trees, as it were. You try to avoid the mountains, right? So it'd be a little bit slower than that to avoid the mountains. Okay? Probably 87 minutes would be good enough to clear everything that's solid. Okay. We've got surface escape speed, all that stuff is already there. Now, if you crush the Earth, okay, make it more dense somehow, okay, say you bring it to this point here where you have got half the radius, 8 times the density, 1/8 focal distance, all of the scale factors that apply to each of the formulas, and that's what you want to be good at, I think, in any sort of physics, but particularly in mechanics. You want to know if somebody changes something by a certain factor, in this case 2, well, I get 2 times the orbit energy, I get square root of 2 times the orbital speed, I get 2 times the surface potential, I get square root of 2 times the surface escape speed, that's escape velocity, that we talked about before, and you get 4 times the surface gravity. The little g gets real big just by doing a half. Okay, so those are things to talk about as you crush to a half radius. So all the diagrams that we were doing that were so nice because everything was just on a nice 1 or 3 units, half units. This is obviously more complicated. So we're getting this great big, as we make this thing smaller and smaller, this thing keeps getting small, more and more narrow, a parabola right here, up to the point where it shifts into the Coulomb potential and force. Okay, now, we've got enough time, I think. We're going to take about 5 minutes extra today because I really want to get through just some numbers that have to do with density of kind of matter that you have in astrophysics, or so we think. With this Earth mass of 6 times 10 to the 24th, density, well, what is that? Well, we've got the Earth radius so we can figure out the volume, okay? And we're talking about here 4/3 pi r cubed. So let's just round that one off to 10 to the 21st cubic meters, and we've got that many kilograms. So we're talking about a density of around 6 times 10 to the 3rd kilograms per cubic meter. That's for the sophomore physics Earth, assuming it was constant density throughout, which it is not. But it isn't too far from the density of liquid iron, which is quite different from solid iron. There we go, right? We got about 1 figure accuracy, right? But we'll take anything at this point, because boy, there's a lot going on inside the Earth we don't. I have in a sophomore physics Earth, but there you're seeing what we're talking about for the Earth is around 7,000 kilograms per cubic meter. Now, you know, per cubic meter of iron, it's a big thing, right? That's what you've got there. Remember, a kilogram, 2.2 pounds. So you got to multiply that 2.2 to figure out how many tons you got there. Okay. Now, what I'll do is a little fingertip physics. This I will skim through fairly quickly here, but you say a nucleus of an atom, atomic weight 50, radius of 3 femtometers. I just picked that sort of out of the air to make a middle of the periodic chart example. And what I'm doing here, if I've got 3 femtometers right there, and I'm talking about packing the mass, where each nucleon, each proton, neutron, roughly 2 times 10 to the minus 27 kilograms, I pack those guys in there, okay, and see, you know, what we've got here. And it turns out to be very close to 1 trillion kilograms. And this is nuclear matter, not iron, okay? A trillion kilograms in a neutron star that's made out of nuclei. Okay? That's a lot of kilograms. Right? So that's what we're talking about. That's my neutron starlet. It's going to be, you know, that big, and with that kind of mass, it's not even going to see the Earth. If I'm some sort of Superman, I can drop that thing here. It's off orbiting or oscillating through the Earth. Just the damping is practically negligible. We could talk about oscillators later on. We'll see an example of that. And the Earth would be crushed by this factor to 300 meters. There's the Razorback Stadium, roughly 100 kilometers just for the football field, but then there's all this stuff to hold the thing makes it about 3 times as big. So we're talking about an Earth that's the size of that. If we take the entire Earth and crush it to that, to this degree, to the neutron star degree, that's how big it is. That's kind of gives you a feeling for how crushed nuclear matter is. The electrons are just out of here. Now, what would you get for the next most dense thing that we know about? Okay, and it's bad enough to crush to 300 meters, but how far do you have to crush poor old Earth to get not this density, but even more than that density for this? So I call the black Earth. Okay. So suppose the Earth is crushed, so that escape velocity that we mentioned back there around page 67 of this particular lecture. Okay. The idea being that I would figure out what would happen if I made the thing so dense that this escape velocity becomes approaching good old speed of light. Now here's a number that is no plus or minus on it now. This is Ken Evenson's measurement of it, taken through the world metrologists and arguing for years and years, and finally deciding that we let this number determine how big a meter is. Because we can measure time so precisely, we cannot measure distance anywhere near that precision. So the whole precision revolution that lets you have GPS and all that kind of wonderful stuff on high resolution spectra that let me do some neat things with my silly theories, that all was possible once we made everybody follow this rule, that is defining the meter. We're not going to have plus or minus on this, probably for a long time, but eventually we will probably, this thing can now be read to 18 figures, so the dam will break at some point, but we don't need to break it at this point. Anyway, using this C here of just 3 times 10 to the 8th, and demanding that speed come here, that is demanding that I get C by solving this equation here for the radius that would be, and you can see that when I do that, first of all I get a bunch of numbers here, but basically I get 8/9 of 10 to the minus 2, 10 to the minus 2. I get a fingertip. So this is the world at your fingertips. Inside one fingertip. That's the density. Earth as big as, well, that's a big finger because I blew it up there. But you begin to realize how incredible are these things that sit at the center of our galaxy. How incredibly they've torn space and crushed it. The electrons are just out of here. They smacked to nothing. Okay, well, this gives you a feeling for what we are up to. Now the next thing that we will do in the next lecture is talk about imagining some neutron starlet, a little fingertip, doing its orbits inside the Earth, which is a model for a lot of things. Two-dimensional oscillators are kind of all over the place, and it's a good idea to get any feeling you can, any way of looking at them is worthwhile. We'll be doing that off and on for the rest of the course, but certainly next time. Okay, any questions that you can think of? Your head questioner here has helped us today, and we appreciate any questions we get. That's the way physics works, right? Somebody asks the question, particularly an embarrassing one, right? That's what you're really looking for, embarrassing questions, because they lead to new results. Okay, we'll see you on Wednesday coming.